hope you guys can see my screen. Okay, is my screen visible to you all? Am I audible or not? And
Yes, Swati, you can go ahead.
okay, thank you. Okay, so today we are going to start sequence to sequence modeling. Okay, one second. Stop sharing. It is not able to use my mouse. So let me stop sharing and start sharing again. Okay, so today's topic is sequence to sequence modeling. Here, first model, which is sequence to sequence. Okay, yesterday what we learned? We learned about first one, artificial neural network, ANN, to RNN, reference neural network, and different types of RNN, one-to-one, many-to-many. And then we learned a special kind of RNN, which is LSTM. So now this is another model which is used for temporal data, time series problems. Okay, so this is particularly helpful when your input and outputs are sequence of sequence. Mostly like in machine translation. You can imagine, as yesterday I also mentioned, that when you translate one language to another, suppose you are saying hello. So if you translate this hello is just one word, but if you translate it to another language, suppose you're translating it to Chinese, so it says ni hao. So there are two words, ni and hao. In Japanese, it will be konnichiwa. There will be three characters, kon, ni, and wa. So in these kind of things, when the input and outputs have varying lengths, you can use this sequence to sequence model. Okay, so mainly it's used for machine translation and then summarization also. Okay, and then question answering, because question and answer length may vary. And what are the benefits? First benefit is this much only, that we can have variable length input and output sequences. Okay, then another, there is one more, like layer introduced in this sequence to sequence modeling, which is attention mechanism. We will discuss it afterwards. But first, let's go with simple sequence to sequence model architecture, how it looks like. So there are two main components in this one. First, we have some encoder, okay, and then we have a decoder. So what is the task of encoder? Encoder will take the input sequence. Suppose this is our input sequence. We are doing machine translation example. So this is our input sequence. It gets the data from here, okay, understands what is the input, and then uh, give some context vector. It will give some hidden states and cell states. Okay, it will give some like understand this part and transform it to some vector and give it to decoder for further translation. Okay, so this decoder will give you the output, like this is a French translation of this English sentence. Okay, so this is the main overview of architecture. Now we will go into the details. what is this encoder and decoder? So first, what is there in the encoder? The encoder's main task, as I have said, it processes the input sequence and encodes it into fixed size context vector. This output, like hidden state and cell state, this makes your context vector. Okay, so sorry. So this is your context vector. Okay, so input is a sequence of tokens. Now we can't directly send nice to the model. Okay, nice won't be understood by the model. These are words. We have to convert into them into some tokens or vectors. Okay, then we can send it to the encoder. Now this encoder itself consists of LSTM cells. There could be another, like it is not necessarily LSTM, there could be GRU cells as well, RNN also. But RNN, these suffer from vanishing gradient problems as we have discussed yesterday. So these are not more commonly used. Mostly they use LSTM and GRU. And the most common is this one, LSTM. So at each timestamp, the network update, like this is the first timestamp. So it gets the input here. Okay, this LSTM will understand what is in the input, and it will there will be some initialization of initial hidden states and cell states. So these are done randomly. These are the inputs for your encoder. So this LSTM takes this random initial state with this input and give you some updated hidden states and cell states. Okay, so and again, then 2 is passed and this hidden state is again updated. Then meet is passed, again this hidden state will be updated, and again we have this hidden state updated here. Okay, and this will be your final output. Now here the individual output from each of these LSTM cells are discarded. We don't use these ones. Okay, these ones are not taken into account for simple sequence to sequence model. Only the final output will be a context vector with hidden state and cell state. So these internal state, this HT and SCT, will be further passed on to the decoder. So this is the internal architecture of a decoder. So this decoder generates some output using this context vector. This is the input from the encoder. Okay, and it produces some context vector, some output at each timestamp. Okay, first this, then this. At each timestamp, it will produce some word. So initial state of this decoder will be the output of encoder. Okay, then it again consists of LSTM cells. Maybe this picture is not very much visible you, but these are also LSTM cells. Okay, like we have in the encoder. So then, like when you pass this state, and then you have some initialization, like we gave some input start at the very starting, then at the very end we have this end as an output. Okay, so we pass this input. This makes sure that decoder understand, okay, now it has to start the translation or whatever task it has been chosen to do. So what it will do, it will take this input, the hidden state, and then this start, and it will give some output. Now the output is produced at each timestamp. And again, there will be some hidden states and uh, that will be updated at each timestamp. Okay. These will keep updating. Then again, it will take this hidden state and this output from the previous timestamp. Okay, it will take these two and give the output. Then again, it will update the hidden state. This hidden state will go to the next LSTM. It will take this output and it will take this output from the previous timestamp and also the hidden state and give you some output. In this way, this sequence goes on. And one more thing here, the main thing the researchers find that now suppose this output was wrong. Okay, it produces, suppose this one ran contrary at the first timestamp. It couldn't understand because initially, remember in the encoder you have initialized the hidden states randomly, right? So because of that, when you start training, this couldn't be done right. Like it could produce another word at this timestamp. But researchers decided that instead of taking this wrong one to the next timestamp, we take the original, we have this data already, right? So instead of taking the predicted value, we will take the actual value as inputs to these LSTM cells at various timestamps. Okay, the main advantage of this thing is that it will reduce the convergence time. So you can reach the minimum loss function faster if you do this. Instead of taking the predicted value, give the actual value to the next timestamp. And also in the this layer, before directly sending it to after LSTM, there will be a softmax function. Okay, so yesterday we have learned about this softmax function. Can you tell me was the function of this softmax activation function, where it was used? Okay, so yesterday we have read that softmax activation function is used in the output layer of multi-class classification. Okay, so in this uh, in this one, you can see we can have Ravi, Tay, Was, and Recontre. We can have four kind of we can say four type of outputs or four classes. So for multi-class, we use softmax function. So here we will use softmax activation function, and it give you probabilities. So it will give you the probabilities of all the words, whatever was in the input vocab, it will give probability of all those words, and whichever was the highest probability, that will be your output here. Okay, so this was one thing. This softmax function will be present at each timestamp. Okay, so in this way it will get the probability. So you have to remember three things here. First, it will take the input from the encoder. Second, while giving the input to the next timestamp, instead of giving the predicted value, we will give the original value, actual value from the input vocab. Okay, third thing, there will be a softmax function after LSTM cell, which will give you the probabilities of all the words. And then based on that, it will give the output, whichever one has the highest probability. So this is a decoder. Okay. This is the same thing, but yes, in one picture you can see both encoder and decoder here. So again, you are giving some input. Okay, and getting some so this is the encoder, this first one, and this is the decoder. So what were the shortcomings of the sequence to sequence model? First, this training requires a lot of computational resources. Okay. Second, it may lead to overfitting the training data. And then it can have difficulty in handling the rare words, like the words which are not uh, some words which are not present in the training data or present like here was to handle long input sequence. Okay, given this one sentence. So if I give you 1 minute, this is a 50-word sequence. Can you translate it in any other language just 1 minute? I think the answer will be no. Even human brains can't do that. So we can't expect the model to do that. In the this model, you can understand we are telling the encoder to remember all the sequence in one go. Okay, we are giving just one context vector as an output to the decoder. So this context vector should hold all the information. Okay, but for long sequence, like researchers found that for 25 to 30 words, if you give a sentence for 20 to 25 to 30 words, then it will work okay. But if it is a longer sentence, then it may not able to give the proper translation because the whole context couldn't be stored in one vector. That is very difficult. So how our human brain work? Like when we see some sentence, we try to do it with small, like we make small things. Like first we will do like this. Okay. And also in this one, when you are learning a new language, maybe you have noticed that we want to keep focus on the main words. Suppose you want to say that uh, like in English you want to say I want to eat pasta. Okay, then if you translate it in other language, suppose I'm translating in Japanese, so you will say pasta or tabetai des. So pasta is the main word. So when you translate it, you will keep a focus on some words instead of the extra words. So here pasta was the main word, then you want to eat. So eat is another main word. Okay, and in Japanese it will be tabe tai. Okay, so you focus on these words. There will be some attention given to these words. Also, another layer which we call attention mechanism. Okay, so in this one, what we do, like in sequence to sequence, the entire input sequence was compressed into a single context vector. Okay, but here we assign some attention weight for each encoder hidden state. Okay, so like here, these hidden states which are present for each LSTM, we assign, suppose we are assigning some weights alpha 1, alpha 2, alpha 3, and alpha 4. And this is done for each of these timestamp. Like for first, for suppose for this one, we assign some attention weights to the hidden states of the encoder. Okay, then these attention weights will change for the next word. For this one, these attention weights will be different depending upon like what is your this word. Okay, so these will change, and again for this one, it will be different. These attention weights will be different. So in total, if you want to produce this, okay, then you will have different alpha at each timestamps, and this is the main like modification which researchers made. So instead of a single context vector, the encode generates a dynamic context vector as a weighted sum of the encoder's hidden state. So these encoder hidden states H, H1 or whatever you want to call HT, these will have some relation with the alpha values. Okay, these are guided by the attention weights. So earlier we didn't take any output from the hidden states. We just have one context vector, but now these are also considered. We are not discarding these. This is the main difference. So how it works? First, we have a query vector which is generated based on the current state or context of the model. Okay, so like this will give you the information that which to which input the model should pay attention to, and then there will be some key value pairs. Okay, so the input representation will be split into these pairs where key will capture the information for relevance and the value will contain the actual data or actual vector or embeddings or tokens, whatever you have. Query will represent the current token, comment, okay, and the relevance score. So here you can see a more complete picture. So this query will be compared with each key to calculate a relevance score. So what are these keys? These are the elements of input sequence. So here like we have these four, four of these. How are you? Okay, these are the elements of the input sequence. These will be converted into some embeddings. Okay, so these are the elements of the input sequence. These the scores will be calculated between this this one and the these input sequences, and that will give you some like a compute you will compute some relevance score, and this score will indicate how much model should pay attention to each part of the input sequence when whenever generating some output. And then this similarity score can be represented as alpha. So for one query, as I have said, for one of these, for like only this comment, you have four alpha values corresponding to the four words in input sequence. Okay, so suppose K1, K2 represent your input sequence, and here we have M is equal to 4. So you will have alpha value 4. And then these relevance scores are passed again passed through a softmax function, which will kind of do the normalization work. It it will do the normalization, and all the scores will have values between 0 to 1, and the sum of all the four alpha values will be equal to 1. Okay, sum of all alpha values will be equal to 1. So What happens then? We have calculated these alpha values, normalized them. Then this value vector vi, this this is the actual value. Okay, so this will be multiplied by your attention weight, and then summing over these values, you will get some output. Okay, and that output will be your like actual value. First, it will be some token or embedding, and then when you decode it, you can convert it to your actual output, actual word. So this is the whole process in attention mechanism. There is one more thing, like usually we do this embedding kind of thing for these uh, these input words, because in embeddings you can store the words in some vector form, okay, in which like the words which are closer to each other, not closer, which are similar to each other, will have similar kind of embedding. Okay, so this embedding could have dimension. You can decide that what dimension it can have, because in if you do in one hot encoding, then like for four it is okay. You have for one word you will have 0 0 0 1, for another you will have 0 1 0 0 1, and for the third one you will have only four vectors if you do one hot encoding. But generally, if you're making some translation app or anything, there could be 1,000 words. I think 1,000 is a short term. There could be more than 1 lakh words, 1 million words, which you have to translate. So in that one, you can't say, okay, I will make one hot encoding for all those 1 million words. So it is better to use this embedding, word embedding. You will learn more about this in the module NLP module. What are these embeddings? So these are just the use cases. First, as I have said, machine translation, text summarization, image captioning, speech recognition, question answering. These are the various use cases. So any doubts till now? Up to now, what we have learned today, we have mainly two models, one model only. The another was added a modification in this one. So it was sequence to sequence model having an encoder and decoder. These encoder and decoders are made of LSTM cells, which have some hidden states, and then there will be one output from this encoder, and this output will be the input of decoder. Okay, so then decoder will produce the outputs at each timestamp, but they have shortcomings. For longer sentences, we couldn't do. So for this, attention mechanism was introduced. So what is the main purpose here? To give attention to some words when you translate some sentence, because at a time you may not need the whole thing to translate one word. Suppose you want to translate this time, okay, you may not need this whole sentence to translate this one word. Okay, so in this way, attention mechanism works for the long sequence words, long sequence sentences. Sorry. So this is the architecture in very short, like how what are those attention weights, how they will be generated, and will participate in the output. So if nothing here, maybe we can go to the coding part. If you have any doubt, you can ask. Okay. If not, we can go to this coding part. As I have said that in these models, the main thing is to understand the architecture and how this is all working. Coding is not that complex. However, in this case, it is a bit complex. How do you understand all these? How do you convert to embeddings and then create those sequence lengths and all? We will see those. So first, yes, I'm using a Kaggle dataset. Okay, so this is English to French translation, or you can use it for another way around, French to English translation. So I'm directly loading the data from Kaggle. Okay, in this one, initially we are doing some pre-processing. We are lowering the lowering all the words in the lowercase. So go will change to goes. So in lowercase we are transforming all the words. Okay, so then we are dropping this is column we don't need license when we are doing our work. So this is dropped. So at present we have only these two columns, English and French. Then this is some like you can say initial steps uh, in analyzing your data. So you are counting the word. Okay, how many total count of English words in in this uh, in this file? So there are 12 lakh, more than 12 lakh words in this table, and distinct English words are only 16,931. 10 most common English words are these. Then we take same as the French counter, total count, count of distinct, and this is 10 most common. This is just like an analysis. This has nothing to do with your model, but it is always good to look at your data to see what is there. And you can also create a world cloud using this. So you can see which words are most common. Okay. So like Tom is most common, think is common, want, no. These are the most repeated words in English vocab, and in French you have these. Okay. Now we come to the our remaining pre-processing part. That was just the basic, but now, as I have said, that you can't just pass the sentence, like pass the word nice or hello to your model. You have to convert it into some numerical form, numbers, vectors, embeddings. So here what we are doing, we are defining a function tokenizer. Okay, here we are first making a list of our words, input text. So this is list of our English words and target is French words. Then we use a tokenizer and this will be fitted on this input text and this will make your input sequence. Here you are assigning one word to one number to one uh, one number to one word. You can see the what is this input sequence. So I have uh, input tokenizer. You can see here what is this input tokenizer. So this will be assigning one number to your one letter. Suppose I is given 1, U is given 2, 2, 3. Okay. Next, this padding, we are applying some padding so that all our input words have similar length. It shouldn't be that one input has more length or one element of the input vocab has more length than the other. So we apply some padding here. And same we are doing for target sequences. And our input vocab size will be, what will be our input vocab size? This input tokenizer, which have these values, plus 1 we are giving because we have added some padding. Okay, so that padding is considered an extra word. So our input vocab size is this much. Okay, then target vocab size is this much. And this is the maximum input length, like how many how many words are there in one of these. Okay, so that will be your maximum input length and maximum target length. Next, again, we split the data into train test split. Same, we are loading it from sklearn. You split your input and target sequences. Okay, then this is like I have said that we provide in the presentation, if you remember, we provide the actual values to the decoder in the next time stamp. We don't provide the predicted ones, right? So for that, we are preparing that sequence. First, we give all the sequence to zeros, and then we are giving this decoder input train. Take it from here and start from after the first, because first will be start, and after that you store this data into decoder target train, whatever is your decoder input train. So this is done only while training. This actual values which I am saying that we provide at the recorder's next timestamp, this will be done only during the training part. So same we do for validation as well. And we define our encoder and decoder. So first we say, okay, input shape, we are not giving any particular shape. We are saying that padding, its length should be like 256 dimension vectors. We are converting these into embeddings. Okay, and then we are giving some LSTM. So it has same number here because it is 256 dimension. Our LSTM has this 256 units. Return state true means that at the output we want the hidden state, right? At the output of the encoder we want the hidden state. So for that we print it return state is equal to true, and then we define this that state, hidden state, cell state, and encoder output. So encoder states will be, which will be passed to the decoder, that is stored in this encoder states. Then we have this decoder uh, decoder architecture. So similar to encoder, we first give shape, then we give the embedding, then we give the return sequence true, and here we also have return sequence is equal to true, that you give the output as well at those timestamps. Okay, so here we have this initial states we have put that when you do the LSTM, your initial state should be equal to these encoder states. Whatever the hidden state and cell state was in the encoder, it should be your initial states in the decoder. And as I have said, we will apply at last activation function, softmax activation function. Okay, so and then we will get the output. So yes, here we can see the model, like here we initialize the model. with encoder inputs, decoder inputs, and decoder outputs. Optimizer, we are using RMS prop. Yesterday we were using Adam, so you can also try with that how it is changing. And the loss function, we are taking this sparse categorical cross entropy. This is similar to categorical cross entropy, as I just mentioned that this is like a multi-class classification problem, right? So that's why we use softmax function in the output layer. So in a similar way, while calculating the loss, we will use categorical cross entropy, as this was the loss function for multi-class classification problem. This part is added. This is mainly to for the embedding one. If you use one hot encoded vector, then you would have used normal categorical cross entropy. So here, yes, you can see the summary, how many parameters are there. You can see for this one, there are a lot of parameters. And here I am fitting the model, training the model. I have given batch size is 1024, epochs only 5, because this model was taking me a long time to run. So after this, it was my GPU limit was over. So yes, if you have good system with good power, with good memory power, good GPU, then you can go for more epochs. It will be good. 5 epochs are not enough. As you can see that I could only reach the loss as 0.7396 for the part, and for validation it is 0.7383. So it is still very high, right? It can be reduced if you want to like make more experiments. Then I will suggest to reduce the batch size as well. Here to run this, it took me I think more than 30 minutes. So yes, you can try that if you have a good GPU. Then we are defining the inference models. So here we have trained our model. Now we have to see how what are the results. Okay, we have seen the loss function, but we also want to see how the results are coming. So for that, we define encoder model, taking encoder inputs and states, and defining decoder model. Okay, and then we have this embedding layer. You can go through these details. Okay, so this is all your inference model. One thing to remember, that whenever you run your model, remember to save it for your future use, because these will take long time and you don't want to lose your data. You don't want to lose what was your output. So always remember to save your models. So I'm saving like this, and then I'm saving encoder model and decoder model also in separate. So yes, here is just like how you can load the models. You can skip this part, because if you are doing it this in one go, then you need not to load the model again. You will already have it in your system, in your current drive. So here we are defining the translation word. Okay, translation functions. So first we give some like start, we give some start input. So the model will know that now it has to start. And this is the decoder model. We are asking the decoder model to make the prediction on the target sequence plus state value. This state value is coming from the encoder, that hidden state. Okay. And this target sequence is the input from the previous timestamp. If you remember that we need two things, the hidden states as well as the input from the previous timestamp. So we give this to decoder model and it will make some predictions. Sorry, give me a minute. Yes. So this is our decode sequence function. Okay. So finally, after doing all this, giving the end function, start function, okay, we are seeing how this is giving the output. So we say hi. So first we are tokenizing it, changing it to sequence, and then then we do the padding, and then we use this decode sequence to get the translation. Okay, so you can see the translation. It is taking many timestamps, and for high it gave something different. So from here you can see that my loss function was too high. It was 0.73. So the results are also not good. That's why I was saying that you can try with more epochs and try lowering the batch size. That will definitely help you if you want to get a good accuracy. So yes, this is sequence to sequence modeling. Now we add the attention mechanism thing in this one. So again we define the encoder in the same way we have done earlier. Then we define the decoder in the same way as well. Then we define an extra part which is attention mechanism. So here we are saying that take a dot product, okay, for decoder outputs and encoder outputs. So these encoder outputs are hidden states, right? And this decoder outputs was output from the previous timestamp, those Q values. Okay, so we are saying that give a dot product, then we are normalizing it. We get the alpha value, then we are normalizing it using the softmax function. Then based on this, we will compute the weighted sum of those encoded encoder outputs. Okay, and this will give you the decoder combined text. Okay, so in the output layer, like um, earlier you didn't have this part, this attention mechanism part. With introducing this, now your decoder outputs will be having this decoder combined context. It is also taking context from the using the attention mechanism. So it is having context, this value, okay, the weighted sum and the decoder outputs. Final output or from your decoder. Then you again define the training model in the same way. Again, I'm using everything same. Optimizer is again kept as RMS prop, and loss function is again this fast categorical cross entropy. Here you can see the total number of parameters is this much. Okay. Here also I'm giving the batch size as 1024. Here I could give more epochs because it was giving a little bit of less time than the previous one to run. But you can see after 5 epochs here, we have 0.7001 value loss, and there we had 0.73. So you can see that after introducing attention mechanism, definitely your loss is decreasing, and also more importantly, the time is decreasing. Okay, so here I had run for approx 15 epochs. After this, again, my limit, GPU limit was over, so it couldn't run more. Again, the loss function is very high. I won't consider this as a good loss. The good loss function should be like 0.1. When we were calculating the loss, it was less than like it was 0.002 or 0.05. So at least I will say it should be less than 0.1 to be considered as a good model. So yes, I will share this notebook so you can try with the more parameters, change the batch size, reduce it, increase the number of epochs. Again, same thing, defining the model for inference. Here nothing is changed. Save your models, as I have said previously, that remember to save your models. Loading models, defining the decode sequence. This is also same as the previous one. And again, okay, we are giving this input sequence and we are asking to translate. It is still giving IU. I think this is also not correct. It has meaning, I think, to have. This is not correct. So yes, so the main focus should be now how to reduce this loss, and that can be done with increasing the number of epochs and reducing the batch size. So here you can see that you are getting these outputs using this encoder model, which you have earlier saved, and then you are loading it. Okay, and the state values are saved in a different list format, and then this will be given to your decoder model. So this decoder model is also you are saving, okay, and loading then. So yes, any doubts here? Today we have covered sequence to sequence models, first without attention mechanism and then with attention mechanism. We have gone through an overview of how they solve work, an overview of the architecture. We haven't gone into detail, but I think this will be a good idea. So any doubts, anything? Module we are left with only one. There will be one more session on GANs, and it will be finished. That will be a short topic. I hope that I will cover that in not more than 40 minutes. So yes, after this module will be over. Anyone of you have done the first day assignment, or you want to ask something? It was on sentiment analysis, the first day assignment. And if you want to ask something from today.
So is the session done, Swati? Hello, I'm audible, Swati? Yes. If is the session completed, Swati? If anyone have any questions, you can ask right away.
Yes, I'm just